All right, so today we're going to talk about probability applications. Now, basic probability is a fraction. Probability applications is a fraction using counting methods. So, to do probabilities using counting principles, you need to make sure that you know the fundamental counting principle. You need to know permutations, and you need to know combinations, okay? So if you haven't seen those videos, if you haven't attended those lectures, you need to make sure you know those three things, and you also need to have watched Fundamentals of Probability or seen that lecture. If you've seen those things, then you can continue, okay? So let's try something, okay? We're going to start with something simple, Mega Millions, okay? So let's say we want to play the Mega Millions lotto game. You have to pick 5 white numbers from 1 to 70, and you have to pick 1 red number from 1 to 25. So the first question is, are there repeats? And the answer is no. If you look at a Mega Millions ticket and you pick the number 7, once you pick it, it's grayed out. You can't pick it again, so there are no repeats. Now, as soon as you see a probability question or a counting question with no repeats, you know you can use one of our 2 shortcuts, permutations and combinations. You have to answer the second question, does the order matter? And the answer to any lottery question is no, the order doesn't matter. And you say, why doesn't the order matter? And the answer is because the clerk has no idea what order you filled those out in, and they always put them lowest to highest. So regardless of what order you filled it out, they always put them lowest to highest. So the order does not matter. So let's take our 5 white numbers, okay? We have 70 white numbers, and since there are no repeats and order doesn't matter, we know this is a combination. So there are 70 white numbers, and we're going to pick 5 of them. So that is 70 C5. Now let's take our red numbers, okay? There are 25 red numbers, and we're going to pick 1 of them. And again, the order doesn't matter, so this is a combination. Now, here's where it gets tricky. I have this. They are independent events. So the fundamental counting principle says multiply them. So I'm going to come over here, and I'm going to find 70 C5. Okay, so take my pocket brain, 70 C5, and I get a big old number, and I'm going to write it down, 121,030,14 times 25C1. Well, 25C1 is just 25, okay? So times, let me just type all this in. Oops, I cleared my screen. Let me try that again, okay? 70 C5 times 25, okay? And that'll give me my final answer. And of course, my final answer is going to be big enough that it's going to scoot off the page. So I'm actually going to bring it up here and write it down. And it's going to be 302,575, 350. Okay? So there's 302,575,350 different ways that I can pick these numbers, okay? Another way to think about that is there's 302,575,350 possible tickets, okay? So this is possible tickets. Crazy, okay? That's our possible ticket numbers, okay? So, number 1 says the winning number matches all 5 white numbers and 1 red number. What is the probability of winning Mega Millions? Now, probability, whenever you see that word, immediately you have to put a fraction. You have to put a fraction, okay? And remember, the bottom number is how many possible outcomes. Well, that's how many possible outcomes there are to Mega Millions, because that's how many possible tickets there are. So that number is going to be 302,575, 350. Okay, that's our total number of possible outcomes. Now, we want to know what the probability of winning is. So the question is, how many winning tickets are there for Mega Millions? And the answer is 1. There's 1 winning ticket for Mega Millions. So the probability of winning Mega Millions is 1 over 302,575,350. If I turn this into a decimal, I get 8 zeros, and 2 threes. So 0.0000000033. Okay? So astronomically small percentage, which is why it's very rare for people to win. Okay? Let's try a different one. A group has 8 men and 12 women. They must elect a committee of 5 people. Find the probability that the committee consists of all women, all men, 2 men, and 3 women. So we're going to do each of these separately. Okay? What do you notice the key word in the problem is? They ask for a probability. So all 3 of these answers must be fractions. All 3 of these answers must be fractions. Okay? So we'll start with the probability that this group is all women. Okay? The bottom number. What do I know? I have, well, let's answer a question first. Are there repeats? So I'm going to come over here to the side. Are there repeats? No. There's no repeats. You can't be on the committee twice. Does the order matter? Well, we've already mentioned if you're on a committee where everybody's equal in power, then the order doesn't matter. So order doesn't matter. Okay, so if there are no repeats and order doesn't matter, this is going to be a combination problem. So I can use my shortcut. Now, if I know that, then I know let's go to the bottom. The bottom is going to be a combination. Now, I am picking from 20 members. It's a total of 20, right? 8 and 12, a total of 20 members. So 20 members, and I'm going to pick how many? 5. Okay, so I'm going to go ahead and type that into my handy-dandy pocket brain. 20C5. I get 15,504. So write that down, 15,504. Okay, now, what is the probability that my group is all women? Now, if I am picking a group of women, I am not picking from 20. Why? Because those people will be excluded, because they do not fit this description. So my top will be 12C5. Why? All women. What does that mean? I have 12 women and I have to pick 5 of them. 12C5 comes out to be 792. And usually when we're dealing with probabilities like this, we give the answer as a decimal. And so we'll take that 792, divide it by 15,504, and we'll get, I'll throw this up here so you can see my answer. And 1, 2, 3, 4. We look to the right, we have an 8, so we'll round that up to a 1. So it'll be 0.0511. 0.0511. That is answer number A. Okay, answer number B, all men. If you're paying attention, you kind of already know where this is going. The bottom is going to be 20C5. Why? We have 20 members, we have to pick 5 of them. Who fits that description? Well, this time we're going to exclude the women because we're only picking men. Men fit that description. So this is going to be what? 8C5. Okay? So 8C5 is 56. And 20C5, we already know, is 15,504. We don't need to type that again. And then we'll turn this into a decimal. And we get a little bitty number this time. We get 0.0036. Okay? So, Where is this useful in real life? Well, this is useful in real life because one of the rules for probability says anything less than 5%. So this would be 5 point, right? Move your decimal 1, 2 places. This would be 5.11%. Anything with a probability greater than 5% or greater is likely to occur. Okay, so if I take this as a percentage, move the decimal 2 places, this is 0.36%. Less than 5%. It's actually less than 1%. What does that mean? This is highly unlikely to occur. So if this happened, there's a mathematical precedent here that this is unlikely and there's a chance this election was rigged. Okay, so that's how we look at things like this. Okay, now let's look at Part C, because Part C says 2 men and 3 women. So if you're following along, we know the bottom is going to be 20C5. Why? Because if I ask you 15 questions about this group, the bottom number will not change because that's the total number of people that we're selecting from. We're selecting 5 people, okay? And of course, we know that that bottom number is 15,504, okay? So we got that down. Now, with 2 men and 3 women, okay? This is where it gets a little complicated, but not a lot. Let's start with the 2 men. How do I pick 2 men? Well, I have to pick from this group of what? 8 men. So it's going to be 8C2. That's going to be my men. How do I pick 3 women? Well, I've got to pick from this group of what? 12. So this will be 12C3. 12C3. And then we go all the way back to the fundamental counting principle. The fundamental counting principle says if you have 2 independent items, i.e., the selection of these men has no effect on the selection of these women, then we multiply them. So we're going to multiply those 2. So I need to know 8C2, and I get 28. And I need 12C3, which is 220. And so then I'm going to multiply 220 times 28, and I get 6160 over 15,504. Okay? 6160 over 15,504, so divide by 15,504, and I get 0.3973. Okay? So, of these 3 outcomes, which one is the most likely? And the answer is C. Why? Because this has a 40% chance of occurring, this has a 5% chance of occurring, and this has less than a 1% chance of occurring. Okay? So that's how we deal with probability. Okay? Let's do one more. We'll stop there. Okay? So a digital lock has the numbers 0 through 9 on the keypad. A 6-digit code is required to open the lock, and repeat digits are allowed. Repeat digits are allowed. Now, as soon as I read that, what do I know? I can't use it's not NCR, it's not NPR. You cannot use those because repeat digits are allowed. Okay? Period. So you can't do anything. Okay? So if you can't use permutations, you can't use combinations, you have to use the fundamental counting principle. Okay? Fair enough? Cool. So, with that in mind, let's keep reading. You're permitted 10 attempts before the lock powers off for 30 minutes. What's the probability you open the lock before it powers off? Okay? What does that mean? You're going to get 10 tries. Okay? You get to enter 10 guesses. So, we're asking for a probability. We know it's going to be a fraction. Okay? So, here's the question. What is the total number of events? Now, what this is going to turn into is the total number of combinations. That's what that's going to turn into. and I have to use the fundamental counting principle to find that. So, the fundamental counting principle, what do we know? We're going to use digits 0. We're going to use digits 0 through 9, which is a total of 10 digits. So, it's going to be 10 times 9, repeats are allowed, so it's going to be, need to erase. Since repeats are allowed, we know it's going to be 10 times 10 times 10 times 10 times 10 times 10, or if you're lazy, 10 to the 6th. Why am I doing this 10 6 times? Because it's a 6-digit code. Okay, so 10 times 10 times 10 times 10 times 10 times 10, or 10 to the 6th, which we know is a 1 with 6 zeros. So it's 1,000,000. You have 1,000,000 possible combinations. Now, the top is going to be the ways to unlock this. Okay, it's going to be the ways to unlock this. Okay, how many ways can I unlock this? Well, I'm going to get 10 attempts before the lock powers off. So my top number will just be 10, given right in the problem. There are 10 ways that I can possibly unlock this. Okay, so that's going to be 10 over 1,000,000, which is going to be 1 over 100,000, or a decimal if they want a decimal. Okay, so in this case, they may want a decimal, they may want a fraction, but the fraction would be 1 over 100,000. Okay, so this is probability applications. I will do a second video with a few more examples. If you have questions, please let me know.